PowerPoint today. Today what I want to do is I want to talk about something called function chart programming. Now, you guys have some experience now with the simulation software and using relay ladder logic to program. Most PLCs are programmed using ladder logic. But there are some other languages and some other methods that you can use to program a PLC. We'll go through a couple, we'll name a couple, and this particular PowerPoint focuses on more of a technique than the language, because you're still using ladder logic. It's just the way you use it is a little different than what you've been shown in the other PowerPoint. So I want to go through that today, and then that'll be it. We'll just have this one PowerPoint, and then I don't have anything after that. As far as the exam, I think I'm going to keep the exam when it is, which is week 8. So you got about another 2 weeks. And sometimes students get a little concerned because this course does have 4 exams. They'll say, well, how in the heck can we do 4 exams and we only have like 4 weeks left? Well, remember, you really only have 2 written exams. So the exam that you'll get during week 8, which will be over the first 4 weeks, that'll be one exam. And then the final exam, which we need to go over a bunch of reduction stuff before you can do the final exam. The other 2 exams are not really exams. One is a program, and the other is just like a research paper you'll do. Not a full-blown research paper, but you'll do some research on something. And they both count as exam grades. So we'll have plenty of time to do the 4 exams. So let's get started with the PowerPoint. And we've talked about basics of programming. We learned the basic symbols for programming, examine if open, examine if closed, and the output energized. We'll learn some other output commands or instructions as the labs go on, as they move forward. This PowerPoint looks at other ways you can program the PLC. You won't do that for us in this class, but I just want you to be familiar with other ways, at least have some knowledge of other ways you can program the PLC in case you end up doing that at your place of employment. So, of course, the most common way is what we said is ladder logic or relay ladder logic. This is where we have instructions designed to look like schematic symbols off an electrical diagram. As a matter of fact, when you write a program using ladder logic, it really looks like an electrical ladder diagram that an electrician can understand. In theory, you can give your program to a plant electrician, and he or she should be able to understand what's going on. For the most part, they should be able to understand what's going on in your program, even though they don't know PLC programming. It's close enough to an electrical schematic to where they can basically see how the system functions. Turns out there's other ways to program the PLC. I list 2 other ways here, and there's also other languages with which you can program the PLC. But we'll focus on 2 other types of language. One is called Boolean language, where you actually use the Boolean function you come up with from your logic to program the PLC. And then what we want to focus on today is something called function chart programming. It's really not a programming language. It's more of a programming approach, and I'll explain the details of that in a second. But let's review ladder logic. This is what we've been talking about and what you've been looking at. So suppose you had this really, really simple hardwire electrical circuit. You got a push button, you got a limit switch, you got a control relays where you're using both the normally open, normally closed contact, and at the very end of the rung, you have a solenoid. And so we'll assume that the blue are the actual addresses. We won't use the address schema. We'll just use the labels to represent the addresses. If you wanted to write this, if you wanted to mimic this in ladder logic, then you might do something like this. So I can use basically these symbols, examine if open, examine if closed, to mimic the functionality of these switches. And if you look right here, we got CR2. We got CR2 down here, which I show that as a basically examine if open instruction, but we don't know without understanding the functionality of this circuit. All we can say about this right now is that we have the correct electrical continuity in my translation down at the bottom, but we don't know if we have the correct logic continuity, because to get the correct logic continuity, we have to first understand how the circuit functions, and we don't have enough information to determine that. So what we did is kind of a instruction by instruction translation of these, and you've done this. This is what you've been doing in your simulation software. So this is what you call relay ladder logic. So we have our inputs on the right, and the rightmost instruction is always our output. Well, it turns out that we can actually implement this in some PLCs directly in Boolean language, or Boolean algebra. And you might wonder, well, how would you do that? Well, we start with our hardwired control circuit, and again, we'll use the labels, but we'll this time we'll give the labels addresses A, B, C, D, and Y. And so if I give these variable names, and I write the Boolean expression for the logic you see here in the circuit, you can see that A and B are ANDed, and A, B, ANDed. That AND combination of A and B is ORed with C, and then that combination of variables is ANDed with D. And so here's the expression that you might come up with if you convert the latter to Boolean logic. And notice that we translated this normally closed contact as a not D. The point of this slide is that in some PLCs, the ones that are designed to take Boolean expressions, you would be able to program this expression directly into the CPU or into the PLC without converting this to ladder logic. And so at the bottom here, and the actual structure of the language depends on the manufacturer of the PLC, but this is kind of a generic way just to think about how you might do this. So you might have one instruction that says start, and it says start, and the start is this PB1, and you're ANDing PB1, since these two are in series, you're ANDing that with CR1. So we're starting with PB1, you're going to AND that with CR1, so now that next command takes these two and ANDs them together, basically to give you this term. And then you're going to OR that, well, you're ORing that with this limit switch. And so you say OR LS1, well, that's this part of the equation. And then it says AND not. AND not means you're gonna not the D, so you're gonna not the CR2, or that we have a normally closed contact. And so in this way, you can actually enter in, without writing a ladder, the logic for a particular rung or set of rungs or program. So the most common way of implementing logic in a PLC is by far ladder logic, but there are some PLCs that understand Boolean logic, and as I said before, the structure might not be like what I'm showing you. This is more of a generic way, just so you can understand as a student how you might do it. But each manufacturer would have their own unique structure that you would use to enter in the command. The point is that you can do it if you wanted to, and the PLC is designed to do it. You can actually enter in logic directly from Boolean into the PLC without first writing out the ladder. So that's the second way to program. The third way of doing this is more of a systems approach. So this is kind of a review. We got the actual hardwire, we got the ladder, and then we got the Boolean. But what you can do is you can use a more structured approach. They call it function chart programming. There's a little history on function chart programming, developed in Europe. You can read through this slide. I'm not going to say a lot about it. This just talks about a little bit about kind of an overview of what it is. But what I really want to focus on is this. If you think about it, any machine process can be broken up into smaller processes, and those processes can be broken up into sub-processes until you get to the point to where you can't break it down anymore. And this is exactly what function chart, here on the slide I said function chart thinking, but function chart programming is the approach where you look at the whole system, maybe the whole industrial process that you're doing. Maybe you're making widgets in the factory. You break each process down into a smaller and smaller process until you end up with a sub process that you really can't break down anymore, and you implement that in logic, the normal relay logic. And so I call it divide and conquer. You just break these processes down, and what you'll end up with, what you'll determine is what we have here, is that you'll quickly learn that when you have a complicated process, basically you're doing things either in sequence or you're doing things in parallel. Events are happening in sequence or in parallel, and even though the overall process might seem complex, the individual steps that make up the process are usually pretty simple. And so function chart programming or function chart thinking kind of approaches the problem that way. You're still using relay ladder logic, but what you're doing, instead of programming one long program, you're making a lot of little sub-programs that you can put together to make the whole thing work. So as an example, just so you understand what I'm saying, imagine that we have this. We have this process. Now this is a really simple process here where we have 6 steps to it. So I'm going to just pause for a second, read these 6 steps to yourself, and then we'll talk about it. So notice now, if you're actually going to program a PLC to do this process, somebody might describe to you in words, or they might actually write out in a paragraph how the process should work. And you, as a PLC programmer, you would have to translate the English to and/or logic and put it in the PLC the right way to get the correct functionality. But notice here we divided the whole process into these steps, and it turned out to be 6. So the operator has to first press the start switch to start the machine, or they can press the stop switch to stop the machine. That's one process. That's one event. The machine will check for a part. If the part is present, the process will continue. If the part is not present, the conveyor is going to move until a part is present. That's another process. The next part, the part is locked into place. That's a process in and of itself. It might be several steps to doing that. I mean, physically doing it. And then the part's going to be stamped or pressed. It's another process or sub-process. And then the next thing, the clamp is going to unlock, and the finished process is going to move out of the printing press. And then the last thing is the process is going to stop. If the machine is in one cycle mode or if it's in continuous mode, it's going to continue on. And so what you would do is kind of like, you're going to start off with this, end up with a stamped part, but all the steps in between you might write out like this, like a flow chart. Each step, think of as a step of a flow chart. And so for the first step, you're going to wait for a part, and then you're going to have a way to check for a part. Now, there's sensors and switches, and there's different ways we can do this. So we're waiting for a part. Maybe you have some kind of robotic arm, or maybe just a system where it falls off a conveyor onto another conveyor. Then you're going to check for the part. Well, how are you going to check for the part? Well, maybe you have some kind of sensor. Either you have an optical sensor, the same type of sensor that you might have on your garage door. If you break the beam, the garage door goes up. You can use that to sense for the presence or absence of a part. You might have each part labeled, and you might have something to read capacitance or inductance. There's a lot of ways you can sense for the physical presence of something. So we're not really looking at how we're doing the function. We're looking at what to do logically when certain things are true or false. So each of these 6 or here 8 steps is a step that you would have in the process. And notice that it's just simply divided out: wait for part, check for part, lock clamp, press the part, unlock clamp, move conveyor, and depending on what mode we're in, if we're in continuous mode, we'll repeat. If we're in one cycle mode, we'll go here and wait for the button to be pressed again. So this is what I mean by divide and conquer. Now, what's going to happen with function chart programming, instead of writing one long rung with ladder logic, what you'll do is you will write a program for each one of these steps. So you have a single program for step 1, a single program for step 2. You have a single program for each step. And you'll have another program that says when you're allowed to move from one step to another. Now, this might seem complicated, but this is actually a really, really, I want to say interesting, but it's a really good way to program. If you ever take actual programming languages, like most languages have a way to do this. If you, for example, if you know, maybe you know C or C++, well, in C or C++, they have something called a function. Or if you have other programs, they might call it a subroutine or an object. Ways to make small programs, and a small program only does a couple things, and you can take those building blocks and build more complicated programs. And this is kind of what function chart programming is. So when you create a program using the function chart system, the steps or individual stages are programmed individually, and the key is without concern for how they will affect the rest of the program. In other words, each of those boxes that I just showed you is its own program. If you wanted to, you can take that box out, because that box, each step does a certain thing. You can actually take that and put it in another program. It's its own little mini program. Now that is that's a big plus, because number one, in computer programming they have something called reuse, and I've already kind of mentioned what that is, where you can use one piece of code in another program. Example of that would be in Microsoft Word. If I want to close the program, in the upper right-hand corner there's a little X. When you click that X, to you it closes the program. But actually, when you click that X, it ends a process in the program that makes up Microsoft Word. And so there's a lot of lines of code just to do that. I know you're just in your mind just clicking the X, but it might be 100 lines of code to terminate the program, to close it on the screen, to do what you do when you close a program. Well, if you notice, Excel, Access, all the Microsoft products have that little X in the upper right-hand corner. Well, what programmers mean by reuse is that X is called an object. And an object is coded, it knows how to close. When you run the code, it closes. And so they're able to take that from Word and use it in any other Microsoft product. Once the code is written, you can use it in other places. So that's one advantage of this function chart programming, is that since each step is its own little mini program, then you can use that in other programs if you need to, rather than reinvent the wheel. If you already have code written that does something, if you use that same process in another manufacturing process, you don't have to rewrite the code. You can just take one of these sections and you can use it in another program. The other advantage is you can think of each one of these steps as a module. And when you have modules, since the module will run regardless of other parts of the program, it makes it a lot easier to troubleshoot. You can make a change in the module without affecting the change anywhere else in the circuit or in the program. So there's a lot of advantages to programming this way. And this is what I call the, this is the POC kind of version of using functions or subroutines. If you're familiar with other computer programming languages, this is the POC attempt to do that. Although they do have subroutines that we'll talk about, there's a way to write a subroutine using a regular ladder logic. But let's get more into this. Let's get into more of the details, and this will make a little bit more sense. Here's another advantage of using this method. Processors that support function chart programming understand which parts of the program are active and only scan the active steps. All other steps are not scanned, thus reducing the scan time. We talked about scan time. You know how important that is. The more instructions you have on a rung and the more rungs you have in the program, each one of those rungs, each instructions have to be scanned. And the more you have, the longer it's going to take to scan the entire program, which slows things down. Well, with function chart programming, the processors know what parts of the program are active and which part are inactive. So unlike just normal ladder logic where you have to scan each instruction, each rung, here certain instructions or rungs will automatically be skipped because the processor knows which parts are active. And so another advantage other than troubleshooting and being able to reuse parts of the program in other places is that the scan time is reduced. And then there's something called an interlock. Now, if any of you are co-oping and you're working in some kind of industrial environment, they have physical interlocks. What an interlock is just a way of preventing something from happening. An interlock could be, a physical interlock could be something as simple as a switch in a cabinet, and that cabinet is lockable. You can tag it out so it can't be moved. You can lock it. An interlock might be a password on the screen. So any way of preventing something from happening. Now, interlocks are important when you design industrial systems because I think I used this example before, but let's say you're writing a program to control an elevator, and you have an elevator that has a dual motor, a motor that can go up or down. It has two coils, a coil for going up and a coil for going down. You don't want both of those coils energized at the same time. You don't want any kind of design mishap to happen to where you can have the up motor and down motor activate at the same time. So you would use an interlock. An interlock is a system to guarantee when one motor is on, when the up motor is, say, activated, there's no way for the down motor to activate and vice versa. So you can use an interlock for that. And so interlocks, depending on the process we're talking about, can you know, they can add a lot of wiring to a physical interlock and a lot of logic or instructions to software interlocks, the ones that you would program. Well, with function chart programming, you don't have to worry about that because basically the processor knows which part of the program should be skipped over or not, which are active or not. So again, it reduces scan time and it will greatly reduce the need for interlocks. So there's so many advantages from this type of programming that you have to wonder why it's not used more. And I think probably as time goes on, more and more people will use this approach because it really is more structured and it's a lot easier to work with. But let's take a look at a generic kind of a function chart program. How would it look? What's it composed of? So basically, function chart programming consists of pieces. The simplest piece you can have is a step and a transition. You can have a step, that's one piece, and a transition is another piece. Each one of those pieces come together. You got to use them together. You can't have a step without a transition and vice versa. So what you're looking at now, this is the symbol for actually both. This is the symbol for a step and a transition. So this part right here is the step. This is the symbol for the step, this box. And the transition, this little line right here is a symbol for the transition. Now, you would actually have this command on your screen, and when you would double click on this box, it would open up a screen over here. Much like in your simulation where you can write your program in your edit window, you can write the program. Well, you would double click on this instruction and an edit window will open up, allowing you to put in ladder logic. So what I said previously is that this function chart programming is really not another language. You're still using ladder logic, it's just you're using it in a different way. And so you're still going to use the examinative open, examinative close, output energize, and any other instruction that we talk about. You're still using that with this function chart programming. It's just how we're using it that's going to be a little different. So what you're going to do is basically, let me go back to this other slide. Each one of these in this process from the example that I gave you, you can consider each one of these a step. So you're going to write code to do this step, and that code will run by itself regardless of what's happening on the outside of it. And you're going to write code to do this step. And again, that code in step 2 will run by itself. But then you're going to write some other code to say when you're allowed to go from step 1 to step 2. Or anytime you go from one step to another, there's code written for each step, and there's also code written that tells you when to go from one step to another. So the actual step is called the step, and the actual program you write to go from one to another is called the transition. And that's what this symbol right here is indicating. So this, again, is just a kind of the graphic symbol for a step. You would double click on this, a screen would open up, and then you would put your commands in here. Now, don't be misled by this. I just didn't have a lot of space, but this is supposed to be a program. You can have as many rungs in here as you need. You know, each step does just one or two things at most. So you'll have the rungs to do that. So I don't have a lot here. I mean, I got this one is not conditional. So the minute this rungs, this is going to go true. And then you're going to read, this is going to read the switches. And so you got these rungs in here for this step right here. You've got that program. Well, once you get it programmed, then you would double click on this line right here, and another screen would open up, allowing you to put in the transition. The transition is the code that says when it's okay or when it's true to go from one step to another. So you double click on this, and you'll open up another screen, and now you can put in more ladder logic to say when it's okay to transition out of this step to the next step. So you might mean, well, the transition, the clamp has to be unlocked, or there might not, maybe there has to be a part in the, if you're using a photoelectric cell to determine the presence of a part, maybe then a part needs to be pressed. Whatever the logic is to say it's okay to go from one step to another, that's what you would program. So the step and transition are used together. You got a step, that's the code that you're going to do in the industrial process, whatever you're doing. And you got the transition, the code that says, okay, now it's okay to go from one step to another. So these are the two basic elements that are used, the step and transition. Well, once you have a step and transition, what you can do is you can put the steps and transitions together and build a more complex structure called a simple path. And you can see how this works. So you would run the program and you would run the code in step 1, whatever that is. Step 1 probably just does a few things. Maybe moves the conveyor up and clamps the part down. And then you have to have code to say when it's okay to go from this step to the next step. Well, that's what your transition does. So you want to make sure, maybe make sure there's a part present, or make sure the clamp's unlocked, whatever the code, whatever needs to happen to go from one step to another, you program it in your transition. So then you have a series, each series of these steps in transition. I got a step and a transition. I got a step and a transition. I can put these together kind of in series to get what we call a simple path. So think of a simple path as just a linear or straight movement through a set of steps and transitions. And this can be a whole program by itself. If you don't have any anding or oring, you're just doing a straight, simple PLC program where you have one event and another. This simple path would suffice, and you'd be able to use this. The beauty of it is if whatever step, let's say, for example, step 2 is something you can use in another program, well, you can just take the code from here and put it directly into another PLC program. Or let's say you had trouble. You want to troubleshoot or make a change in step 2. You can do that, and since this program runs by itself without affecting what's outside of it, you can make changes in here, and you don't have to worry about the changes affecting some other part of the program. So the simple path is the first structure that we can use and we can build out of a step and a transition. Well, then the next structure we can build is called a selection branch. I'll be quiet for a second, and you take a second and read this, and then I want to read it. The selection branch. Okay, so whereas the simple path, you run the code in a step, and then you check to see if the transition is true. If the transition is not true, you'll run this again, and you'll check to see if the transition is true. If the transition is still not true, you'll run this again. You'll keep running step one until the transition is true. When it says it's okay to transition from one step to another, when this is true, then you'll transition to step two. You'll run the code in that one, and you'll keep running that until you transition to the whole thing. Well, the selection branch is a little different. What happens is you'll run the code here. And then what this will do is once this code is ran, it'll run and see, now you got to transition into a step. So once the code here is ran, you got to transition into either this one, or you'll transition into that one, or that one, or that one. You only go into one of these. You can't back out and go into another one. So the first true transition, the first one of these is true, is the one you're going to transition into. So this is equivalent to an OR. The first true you get to is going to give you a true output. With the first true transition you get, you're going to transition into that step. So if you're using this instruction, which one would you want to put first? Which one do you want to put to the left most? Because these things will scan from left to right as they scan. You want to put the one that's most likely to be true, or the one that's most likely to be false. Well, either way will work. If you're trying to increase scan time of the PLC, then since this is going to fall into the first true transition, the one that's most likely to be true, you want to put that further to the left so it hits that one first. And again, you don't have to do that. I mean, if you're not concerned with speed. But if you're concerned with speed, what this is looking for is once we run the code in this first step here, it's going to look to transition into one of these. So if this is false, it's going to then scan this one. If this is false, it's going to scan this one. If this is true, it's going to fall into this and run this code. It's going to continue running that code until this transition says it's okay to transition out. It'll run that code, and then it's out of the structure. So this is like an OR, and it's looking for the first true transition in, and then it's looking to transition out, the selection branch. So we got the simple path, we got the selection branch, and then the other structure is called the simultaneous branch. And I'll show you this in just a second, but take a second and just kind of browse through this real quick. And what you want to focus on here is AND logic. So I'll be quiet for a second. You just kind of read this PowerPoint to yourself. So the simultaneous branch, whereas the selection branch, the way we said this works is that you run the code here, and then you're going to transition into the first true. If this transition is true, you'll transition into this step, you'll run that code, and then if this is true, then you'll fall out of the structure, you'll run that code, and then you're done. You never back up to go to these other steps. Once you transition through, it's just one way in and one way out. Well, the simultaneous branch uses AND logic, which means with AND, all the conditions have to be true. And what we mean by that is, let me show you the structure. Here's the structure for it. Every one of these branches have to be true before you can transition out. So let me show you the example problem so this makes a little bit more sense. So here, this is equivalent to AND logic. It says 2 or more parallel paths must be scanned at least once. The important one is the processor finishes running the simultaneous branch when it has scanned each step in each path at least once. And the common transition is true. So they all have to end up being true. So read this example to yourself and make sure you understand it. And this right here, PCB, that stands for printed circuit board. So take a second and read that. So in this industrial process, we're making computers, PCs. And for this particular part of the process, it says assume that you're mounting parts on a printed circuit board called PCB1. So you got printed circuit board 1. And at the same time, you're soldering on another printed circuit board, PCB2. So you got 3. You got printed circuit board 1 that you're mounting parts on. You got PC board 2. It's already had the parts mounted on it. It's being soldered. And then you got the motherboard, which is waiting for the other 2 boards to be plugged in. And all this is being done automatically. And so how would this work using the function chart structures? Well, the selection branch. You want to make sure all the events take place. You got to have the first circuit board parts mounted. You got to have the second one soldered, and you got to have the motherboard there working. All those have to be true before you start assembling it. So the selection branch will be ideal for that. So the way this is going to work is you got your code here where you got to transition into the structure. So you're going to transition into the structure. When you transition into the structure is going to run this. So it's running this code. It's running this code. It's running this code. Now at that point, each of these in the transitions are independent. You're going to keep running the code here until it's true to transition out. So you're going to make sure all the parts are in place or whatever you have in that particular sub-process. And the same over here. Eventually, though, you'll transition all the way down to here. And this will transition all the way down to here. And this will transition to here. And then when you transition out of these, all of these have to be true. In this common transition, all of these have to be true before you can transition into here to do the assembly and transition out of the structure. With just one of these being false, is going to hold you up and keep running that particular branch until you have all true transitions. So that's why this acts like an AND, because all branches have to be true in order for you to get a complete, or to transition out of the complete structure, or you can say for the complete structure to be true. And so programming this way has several advantages, some of which I mentioned already. I like this first one that says with function chart programming, the description of the problem becomes the actual program. In other words, when they hand you the description of the problem, and you let's say you flow chart it, like I showed you in the second slide that I showed you today. Each one of those parts of the flow chart becomes a little mini program. So just by understanding the problem and describing the steps, you're basically defining the program and doing that. That's a big advantage. As I mentioned before, troubleshooting is anytime you have something that's modular, then troubleshooting is a lot easier. Modular electronics is a lot easier to troubleshoot rather than having everything integrated. Well, the same thing works in software. When you have pieces or parts, it's easier to fix stuff if it's not meshed with other stuff. So troubleshooting is a lot easier. So you can read the advantages. I know when I have quizzes and all of that, sometimes I ask about advantages and disadvantages. So you can read these. It should be, a lot of this should be self-evident. The programming is going to be simpler. Scan time is faster because you skip over parts. Processors automatically understand which parts are active and not active. Since you're dealing with modules, which is a program that runs independently, you can move the module around or make changes. So easy to maintain and easy to add other modules to it or take modules away from it. So these advantages should make sense. And again, we don't use function chart programming. As mentioned, the actual book that I used to use for your class mentioned function chart programming, probably because you'll probably see or hear about more and more and more of this technique, because it is a way more cleaner, a more structured approach to programming. And so that's pretty much it for this. just on the side, we mentioned ladder logic is by far the most common. You can program PLCs using Boolean algebra directly. And now we looked at function chart programming, which is not really another language. It's more of an approach, still using ladder logic, but the approach that you use is different. But you can program PLCs in other ways. There's something called a state diagram that they use in digital electronics. You can use that. These are all languages here. Basic programming. I think that stands for beginners, all-purpose, symbolic instruction code. Basic programming language. It's like a programming language for beginning programmers. C, and a high-level language is any language like you might be used to, like Python or Fortran, any language that uses English words for the instructions. So you are able to program PLCs in other languages, but again, by far, most PLCs will use ladder logic, like what we're learning in this class. So that's pretty much it for the PowerPoint. Now, I don't know when this comes up, this information. I don't know. I got to go back and look at Quiz 7. If you signed on to the class late, I mentioned that Quiz 7 accidentally got published. It wasn't supposed to be published until the actual end of the week. I will go in and change the questions or update the questions in some kind of way. It got published. It's like 3 students actually took the test. They didn't do very well on it. I think most people didn't do well on it that took it. But you weren't really ready for it. But because you took it, the system wouldn't allow me to unpublish it. Once the student takes it, it's got to stay in the grade book. So I got to go into the grade book and figure out what I'm going to do about quiz 7. I got to go in and, first of all, get the people that took the test. I'm not going to count. Those grades won't count. I'll go in and some kind of way have to redo quiz 7. So what that means for you is, for right now, lab 2 is posted. Focus on lab 2. You're going to just practice some programming. You got familiar with the instruction set in the first program. You want to practice now putting programs into the simulation software. So that's really all this lab 2 is. So you'll practice that. So focus on that, and I'll figure out by the end of the week how I want to handle quiz 7. Just look for my announcement so you know what to do with quiz 7. One more thing I want to say, guys. Now, I graded on Sunday, and as of Sunday, right before midnight, I think only like 4 people had turned in their lab. If you turned in your lab, it's graded already. If you turned it in yesterday, it's already graded. If you turn it in today, it probably won't be graded till towards the end of the week. But I'm only bringing it up that you don't want to wait. I mean, the idea is, and I know you guys are going to do what you're going to do with your time, but the idea is we're not meeting on Wednesday and Friday, so you have time. You can use that time to work on your PLC stuff, your programming. I could care less when you do it, but don't get in the habit of waiting till the day before it's due to do it. If you do that, you're going to run into trouble because some programs are not going to work. You might have to debug them. I mean, if you wait until like the day before, you're going to end up rushing and not getting out of the course what you should get out of it. So you got time. Today we're meeting. We won't meet on Wednesday. Well, then just take that hour to look at the next lab and maybe do it. Don't try to do it all in one day. If you do it all in one day, right before it's due, you're not going to absorb the information. I mean, you guys know about cramming. You can't cram. Cramming is not like actually sitting down, taking time to study it and go through it. The class is not a hard class. I mean, I've been teaching this class since, probably 1999, and I think I'm only given 1 F, and that student tried really hard to get the F. Most people get A's or B's in this class. I'm not saying it to say you don't have to give it attention or try. I'm just saying it's a fun class. I designed it that way on purpose. You're going to get a good grade if you do the work, but I want you to get something from it, and this is one class that you can actually learn something in one class and go out and use it right away. Not all classes are like that. So to get the most out of the class, take it seriously. I understand people have time constraints and all of that, but when I think I have 33 people in the class, and when only 4 people have their exams, have your program in the night before the day is due, I just don't want everybody to wait till the last minute to try to get it in. So try to spread it out a little bit, and as we go through, I won't say the programs become particularly tough. They become a little bit more involved, though, and you don't want to try to wait to the last minute to do it. The other thing is I had, one or two people had issues with the program. I think one person may not have operated the wrong operating system or something like that. Well, this is the reason why, 2 weeks ago, I had everybody, I told you to go to the website, download the free version and play around with it. And there's another reason why you don't want to wait till, the 11th hour to do the work. Any technical issue you have, you want that to be already worked out so we can hit the ground running. Because I'm telling you, the next 4 weeks, we'll go through it real quick, and before you know it, we'll be meeting 3 days a week again for the last part of the semester, and then we'll be done and it's over. And I want everybody to get a good grade. So, just, try to do the stuff earlier in the week. That way, if you have any issues or whatever, you have time to work it out. And you won't, and definitely don't miss the due date, because I'm kind of a little bit more lenient with the other stuff, but with these labs, you got to get them in on time. So that's pretty much all I have. I got a couple minutes left. Let me pause for a second. I'll turn the camera on. I don't think I have it adjusted correctly, but I was just using the microphone on it. Let me pause to see if anybody has any questions in general or any questions for me. Anybody have any questions or comments, concerns, thoughts, suggestions?
Yeah, so I'm one of the people that are still working on Lab 1, and when I went to...
Wait a minute, hold on. Okay, say that again.
Okay, so I still haven't turned in Lab 1, and I checked out the instructions for Quiz 6, and it said, it's best to finish Lab 1 before you take Quiz 6. So I figured they were due at the same time, but I looked earlier and saw that Quiz 6 was already closed. So, yeah. I mean, I could just take that as one of my drop grades or something, but...
No. So let's do this, because here's what I'll do. Because the only reason if you took the quiz already, it was pretty easy. But I felt like I want everybody to get an A on it. You probably could have did okay without Lab 1. It's not that bad. But if you go through Lab 1, I almost guarantee you'll get 100 on it. That's what I was looking for. But I had you missed it, and then I had another person that had an issue with the
Honest as well, yeah.
Yeah, with the opera. So what I'm going to do is I'm going to extend just this one time. I mean, it is the first week and things happen. So I'm going to open that up again, and I'll extend it. So if you missed the due date, you'll be able to get it in. But did you take the quiz? Everybody take the quiz? Anybody not take the quiz? Okay, so we're good on the quiz. I'm going to open the lab up here in just about when I get back to my office. It'll take me a minute.
Wait, no, I didn't take quiz 6, if that's what you're asking. I thought that
Yeah, okay. I'm going to extend those. I'll extend those in about 30 minutes. I'll extend it maybe till tomorrow or something. I'll extend it, and that way you can finish it up, get it in. But then going forward, we want to make sure that that we meet those deadlines, because I don't, I don't want anybody to get a bad grade in the course, but you got to meet the deadlines for the lab. So, so I'll within the next 30 minutes, check Canvas. I'll turn that back on. You'll be able to upload it, and I'm just going to extend the time until tomorrow. Now, you guys that did it on time, thank you for doing that. I wish there was a way I could reward you, but just keep doing it on time and turning it on time. And, things do happen. So I'm hoping that the person, I think somebody had an operating system problem or the wrong PC. I'm hoping they sent me a text saying that they would try to find. So I'm hoping that's enough time for you guys to get all the bugs worked out. If I make this due at midnight tomorrow, does that help everybody out? Or is anybody still in any kind of situation they can't get out of? Okay, well, I'm assuming that'll do it. So I'll go in and I'm going to extend quiz 1 and lab 1 until midnight tomorrow. And then you guys should be able to get it finished. Lab 2 is already out there. Nothing too difficult. You'll need your lab manual for this one. Go through and you'll just put some stuff in the PLC, and then it'll be hopefully another 100 points. So anybody have any other comments or questions?
I have a question on quiz 6.
Yeah.
So for
wait. So
Oh yeah, they didn't take it. Okay.
yeah, tell you what, send me a text and text me your number and
Okay.
I'll call you. Just send me your number and I'll call you from my office.
All right, sounds good.
My phone, because I'm gonna go in and open that back up, and I don't want anybody else have something that's not on quiz 6.
Well, I was just gonna say, is it question 6 that he was asking, that you're asking about?
Yeah, yeah. Question
Got it.
Is there
six.
something wrong? Is there something wrong with it, or is there would that? If you tell me about it, would it be giving anything away or not?
It
I
just
could like
might-
explain it without. Yeah, I could explain it without. I just you have to input a word basically, and I put like 2 words instead of the
Oh,
one word.
okay. Did you get it? You think you got it right, but because of the way the question was structured, it might have marked it wrong?
Right. Yeah. I accidentally
Okay.
like put another word in it.
Okay.
If that
Yeah, it makes sense. Oh,
Yeah.
is anybody else in that same boat other than those 2 students that just? If you're in that boat, send me a text right now, and when I go to my office, I'll go in and I have to grade yours by hand. But make sure you say, hey, check my quiz 6, question 6, and I see it, I'll go in, and I got to go through each one by hand. It takes a while, but it's easier if I have a list of students' names for me to go by. So question 6, and then anybody else, oh man, I don't know if I can change that. Well, I think most people probably have already taken the quiz, so it should be all right. So if you think you messed up question 6 because of that reason, send me a text and I'll fix it here in the next few minutes. Anybody else? I'm sweating, guys, because I'm in a room and the air conditioner has been off all morning. It's like 90 degrees in here. So I'm like drenched. But anybody else have any questions or concerns or thoughts? Somebody send me a message. Okay, yeah, right. Okay, so Ryan said he did the same. So I'll go in and fix all that. So number one, I'm gonna extend the due date for lab 1. I'll extend that. I'll extend the quiz, and then I'll go in and I'll check question 6. And if you send me a text, your name, check my question 6, I'll go in and I'll add those points by hand. Does that cover everything? Anybody else? Because I won't see you till next Monday. Anybody else have any questions, thoughts, concerns? When is the lab due now? So I'm going to make the lab due. Is tomorrow midnight? Would that be okay for everybody, or is that not good enough?
Absolutely.
Yeah. That's fine.
Okay, everybody says that works. So we'll extend everything to tomorrow midnight. Okay, and then okay, great. Thank you, guys. All right. Well, if anything comes up, just send me a text. I'm going to go work on the grades now and updating the Canvas. And you guys have a great rest of the week, and I will see you in about a week.
Can I
Thank
ask a
you.
quick question about Lab 1?
Sure.
So for number 3, are you okay if we just fill out the table and put that in, or do you actually want to see something else?
Some people just show me the table, and some people show me the table and the switches. The table's fine. I mean, I just want you to know how the table and the switches kind of how they connect to each other. So the table, I'm cool with that. Just send the table.
Okay, thank you.
All right. Okay, guys. Well, thank you. And if anything else comes up, you can text me. And yeah. Okay. Thanks, Sam. Jack, thank you. You're nice too. Thanks. All right, guys. Thank you. And I'll see
Thanks.
you
Have
later.
a good one.
Bye-bye.